showing what the graph looks like. And I would encourage you as a student, back when I took calculus, we had calculators, but they weren't this is so much better, frankly.
For sure.
So occasionally I'll refer to this, and I'm just going to take a snip and go back to my other screen, and we're going to talk about what limits mean, or just review what limits mean. So to actually determine a limit, there's a lot that you have to do. So the limit exists, the limit as x approaches like a number, in this case 0, from the right of your function, which in this case is the x over absolute value of x, whatever that number is, has to also equal the limit as x approaches 0 from the left, f of x. So in your problem, what you really need is the limit from the left to equal the limit from the right in this case.
Gotcha.
And they have to be the same. Now, graphically, can you tell me what you see graphically here? Actually, that's not defined there.
Okay. So what do I see graphically? I see that there, like, for example, I don't know, there's two, obviously the two lines, one is going from 0 to infinity and one from 0 negative infinity.
Yes. So I've labeled some arrows here from the right and from the left, and that's how you have to interpret it. You're actually literally tracing along the curve from the right, literally tracing along the curve from the left. And we'll get to how to do this algebraically, but just looking at the graph, the limit as x approaches 0, and the positive here means from the right, it approaches the y value of 1. The limit is always the y value. Okay. And then from the left, that's this negative to the right of the number, it approaches -1. And the problem is that these numbers are not the same. Okay. And since they're not the same, the limit does not exist.
Gotcha.
Give me some feedback on that. Is that clear? Is that not clear?
Yeah, no, it is clear. So it is just like a basic function. I'm just gonna have to treat it just like, I don't know, like a
this one's special.
Function.
This one's special.
Yeah.
I mean, it's different. Yeah. It's weird. It's a great test question, I guess, if you know. Okay. But I mean, I don't write your test, but I mean, it's good. It's an interesting thing. Let's talk about how to do it algebraically. Now, it comes from this right here. Okay. So how to do it algebraically, because maybe you don't have Desmos on your graph or your exam whenever you get that. So from the left, when we're doing something from the left, notice that x is less than 0.
Right.
From the left. So that means that instead of saying the limit as x approaches 0, sorry, let me go from the left here, x over absolute value of x, it's really the limit as x approaches 0 from the left, x over negative x. And that, and you're like, wait, why is it negative x? Well, it's because the way it's defined when x is less than 0 is this.
So we're going to have to put like the negative sign just to show it's approaching from the left.
Well, it cancels. So you can cancel out the x's.
Okay.
Like that. And then you have the limit as x approaches 0 from the left of just -1. Well, whenever it's just a number, the limit equals that number.
Gotcha.
Okay. If it's a function, you try to put the number in, but there's no function left. So that's why it's -1. Now that's consistent with our graph. Our graph here says it's -1. Okay.
Right.
So now it's not kind of underwhelming, but from the right, it's the same deal. Limit as x approaches 0 from the right, x over absolute value of x. Now, because we're going from the right, we know that when x is greater than 0,
it's going to be positive.
It's positive x. Okay. So it becomes x over x, limit as x approaches 0 from the right of 1 equals 1. And because those are not the same,
limit does not exist.
Yes. Okay. So they make more sophisticated problems than this.
Right.
I'll briefly,
yeah.
It's the same idea. Like let's just say x absolute value of x minus 2. This is a piecewise function where it's x minus 2 for x greater than 2, and it's minus x plus 2 for x less than 2. So if they again want the limit as x approaches 2, x minus 2 over absolute value x minus 2, you do exactly the same thing that we just did in this problem.
The algebraic
Yes,
method.
you have to
Okay.
substitute the equivalent form in for it.
Gotcha. So if I'm gonna do it, for example, like when the limit, when we're trying to take the limit when x approaches 2 from the left, it's gonna be, then we're gonna write next to it x minus 2 over the absolute value of negative x. Why did
Well,
you write plus?
so you substitute in the form for when it's less than 2.
Oh, gotcha. I
Yeah.
go back to the parent function
Yes.
per se. Okay,
Yes.
gotcha. Then you substitute and whatever. Gotcha.
Yes. Now, if it's not clear, just like the way I wrote the one on the bottom is I just negated both of them.
Gotcha, which makes
And
sense.
and that's consistent no matter how you're doing these things. I mean, one goes down, one goes up. They're just negatives of each other.
Yeah. You just pretty much multiplied it directly.
Exactly.
Gotcha.
Exactly. So like the reason I'm asking for it at 2 is because that 2 is that break point. It's like the weird point. Okay.
Mhm.
Because if I ask you in a separate problem, if I asked you the limit as x approaches 3, absolute
Mhm.
value, I'm sorry, x minus 2 over absolute value x minus 3, sorry, 2. Sorry, it's really bad. Let me I'm just trying to make a point here and I got messed up here. So at 3, you just put the number in and it works.
Right,
But at
right.
2, the issue is at 2 is you get division by 0, and that's when you have to
Which is
use another.
undefined. Right.
Yes.
Gotcha. Okay, that's fair enough then.
All right, so we should do another problem. We should do, I'm sorry, move to continuity. We should move to continuity next.
Perfect.
Is that okay?
Yes, please. Yes.
Spend a few minutes on this. Okay, so continuity. The definition from like before calculus is like you can write it or you can draw the function without lifting up your pencil. So it's like something like that. That's continuous.
Okay. No
Okay.
holes, no jumps, none of that.
Right. So let's talk about so it's actually one of those things where we have to talk about what are the discontinuities so you know what to look for. And you mentioned a couple of them. Holes, jumps, vertical asymptotes. And these violate that first condition. So now the only removable discontinuity is a hole. You can remove a hole as needed in some of these problems.
Okay.
But jumps and vertical asymptotes you cannot remove.
What do you mean by remove?
So you'll get a problem. You'll get so let me make a graph here. So you get something like this. There'll be a hole there. And this is at, I don't know, we'll just say it's at 5. It'll ask you, this is f of x. Is f of x continuous at x equals 5? The answer is no. It is not continuous because there's a hole.
Correct.
Can you fill in that hole? Yes. If you fill in the hole, it changes the answer to
continuous. Gotcha.
yes. Okay. But if I give you a different function, like the one we just were working with, it's actually a perfect example. Is this one continuous at x equals 0?
No.
No. Can you make it continuous?
If the circles are closed, or at least one of them.
But it's a jump. There's no way to fill in a jump.
Gotcha.
There's no way to fill in a jump.
Gotcha.
And the analogy I often make is to like a river. You know, if there's no bridge, you can't get to the other side.
That makes sense.
Yeah.
Makes sense. Okay.
Now the last one is a vertical asymptote. Okay, so here's your graph of like y equals 1 over x squared, something like this. And it's like is f of x, I guess they're functions, but f of x continuous at x equals 0, and x equals 0 is a vertical asymptote. The answer is no. Is there a way to make it continuous? Is there a way to make it so that it's essentially it's actually very similar to the jump here. It's just a jump in a different direction, but there is
Right.
no way to make this continuous.
Yeah, since that vertical asymptote is in between the two lines, I
Yes.
guess there's no way. Gotcha.
Yes. So here's a question you might see. You might get something like let's say f of x equals x squared minus 1 over x minus 1, and you would being a good pre-calculus college algebra student would recognize that the numerator factors as difference of squares, the denominator factors or does not factor, but it cancels, and this has a hole at x
equals
equals
1.
1.
Yeah.
So when you graph this x plus 1, which is just a boring old line, at 1, there's a hole. There's a hole right there. And your calculator doesn't always show it. Like if you use that Desmos thing, you won't always show it. But
Yeah.
the problem would be written such a way where it'd say determine, so it'd be written like piecewise. It would say this first one would be for x not equal to 1, and it would say what does x have to equal at 1 to be continuous, and you would say 2, and that's what allows you to fill in that hole.
That makes sense.
That's sort of a test question, I guess.
Gotcha. Yeah. So yeah, pretty much what I'm really worried about. And thank you, by the way, for the
Of
explanation.
course.
Yeah, but yeah, eventually, like I seen one of the like eventual questions where it's gonna look like, so they'll give me like a function, and they're gonna ask me to find the vertical asymptote, the limit from the left to right, the eventual, like the final limit. Is it gonna be continuous or not? And stuff like that. So basically, one function that's going to ask me pretty much everything about the first section, if that makes sense.
Yeah.
Right before we get into what is it? Differentials,
Derivatives.
derivatives. Yep, derivatives.
Yeah.
So that's pretty much what I'm trying to get out. And obviously, one of them is going to be like this: the absolute value and the continuity and discontinuity. So
Yeah. So the next kind of related thing here would be like limits at infinity, which is, and then like you were asking about vertical asymptotes
right.
a little bit here. So let's take a function like f of x equals just 1 over x, something very basic for the moment here. And the graph of this looks as looks like the following. Looks like that, and then that. And so there's like 4 questions I could ask you. I could say, what is the limit as x approaches infinity 1 over x? So this is the limit at infinity as x goes to infinity. And the wording that I want you to think about is it going in this direction to the right. To the right.
Okay.
So if you trace that thing to the right forever, what y value does it approach? Is the
Y
question.
value?
Yes, it's the limits are always the y value. This number or thing on the right here is always a y value.
Is it going to be 0?
Yes. Okay. So I could similarly ask you, what is the limit as x approaches minus infinity of 1 over x? Now, another technique that students like to use, which I don't like as much, but it does work. It's like imagining putting in a really negative number in for x, like negative 10 billion.
Okay.
What is 1 over negative 10 billion? Well, it's essentially 0.
0. Gotcha.
And if you have a calculator, some students actually put that in. They'll put like 1 over 10, 1 over 100, 1 over 1,000, until they convince themselves that it approaches 0.
0. Gotcha.
Okay.
Okay. That makes sense.
But
So
now there's go ahead. Sorry.
I was just going to say, therefore, the limit is going to be 0.
Yes. Now there's 2 other questions that are reasonable to ask you about this graph, and they have to do with the vertical asymptote. It's the limit as x approaches 0 from the right, the limit as x approaches 0 from the left.
Okay. So from the right, the graph is going up, which is going to be infinity, and from the left is going to be negative infinity.
Exactly. Yes.
So there's no limit at 0.
Right.
Gotcha.
Okay. Now, just you in your text you wrote you're asking how to determine vertical asymptotes.
Correct.
I'm
Yes.
sorry. Yeah. Okay. All right. Okay. So let me give you a couple of example problems. So the first one, again, very basic here, is like something like 1 over x plus 2. So the vertical asymptotes occur when the denominator is equal to 0. Okay, so you literally set the denominator, whatever the denominator is, equal to 0, solve for x, and that is your vertical asymptote.
Oh, just like the pre-calc then.
Yes, but this is
Oh.
like 80% of the time this is true, meaning there's
Okay.
exceptions that we need to cover.
Gotcha. Gotcha.
Okay. So like just generally, like if you only cared about being a B student, and I think you probably want to do better than that, is what I'm understanding. Like this I would just say always set the bottom equal to 0. But what
Right.
if you have something a little bit more complicated, like x squared minus 5x minus 6? Okay.
That's a trinomial, right?
Yeah. So
Or,
you would have to be able to factor this.
gotcha. So which is going to be x minus 3, x minus 2? Or
So that
plus
does
2?
not get you to minus 6. Yeah, this is,
Oh, x minus 3, x plus 2.
so I'm gonna,
Or no, still, oh, minus 1. Okay, gotcha. And 6. Well, it has to be 2 and 3 if we're going to get 5. Or no,
nope.
negative 6, 1.
There you
Yeah,
go. There you go.
negative
Okay.
6, 1. Gotcha.
Easy to mess that one up. So this one has 2 vertical asymptotes, but it really isn't a violation of what I just said. It's you really do set the bottom equal to 0, but it could be more complicated than just setting it equal to 0.
Gotcha, gotcha. It's just
Okay.
going to be more of the very work per se.
Yes. Okay. Now we move in, and actually let me give you, so in this first problem up here, like if I had said plus 7 over here to the right, it still doesn't affect this. You still set the bottom equal
Same
to 0.
process.
Yeah.
Gotcha.
Okay. Now let's get into some exceptions. Let's say I give you something like this: x minus 2 over x squared minus 4. And I ask you about the vertical asymptotes. So there's really in pre-calc, they might have called it like a 7-step process or a 10-step process. You
Right.
want to factor the numerator and the denominator.
Yeah.
Okay. And if you can cancel a term, okay, or a factor in this case, sorry, factor is not a term. If you can cancel a factor, this results in a whole. We already saw that earlier. Okay.
Correct. Yeah.
So that kind of goes against what we just talked about, because there's a whole at x minus 2 equals 0 or x equals 2, not a vertical asymptote. So it's not always the case that you set the bottom equal to 0. You do after you determine the holes. Holes come before vertical asymptotes.
Vertical asymptote. Gotcha. Gotcha.
Okay. Now, what is left over in the numerator after you cancel out these factors?
1.
1. Very good. So this one has a vertical asymptote when x equals minus
Negative
2.
2. Perfect. And that's because we figured out the whole at first.
And you got to be careful about some other situations, like, because I don't know I know you said it's a self-paced guided thing, but you get a range of instructors in this world
Sure.
where they put stuff on the bottom that looks like it should have a vertical asymptote, but it doesn't.
Okay. Well, that's not factorable, right?
Right. But you might look at it and try to make it work, and
Gotcha.
you got to
It can
be
be a little tricky. Yeah.
you got to be very careful here. So vertical asymptotes come after that, come after the holes. If you can remember that, that will be everything.
Beautiful. Beautiful. Excellent. That makes sense.
All right. So let's look at a couple other problems here. So limits at infinity. So the limits at infinity really are about determining horizontal asymptotes.
Okay.
We've kind of, there's really like three cases. The first case, and I'll just give you an example, we've kind of already looked at it, is like f of x equals 5 over x plus 3. Okay, so the limit as x goes to infinity of this function, if you put a really big number in for x, you add 3 to it, 5 over a huge number ends up being 0. And that's consistent with what the horizontal asymptote is. So in pre-calculus, you learn to look at the degree of the numerator and the degree of the denominator. Do you remember
Okay.
that?
Yes, I do. Yeah.
Okay, so if the degree of the numerator is less than the degree of the denominator, and that's based on the exponent of the x term,
Right.
then it's always y equals 0. Like your horizontal asymptote is always y equals 0. Your limits also approach, sorry, it's negative infinity. They also approach 0. They always approach the horizontal asymptote.
Horizontal. Yeah, that makes sense.
Okay, so that's case one. Case two, and so in pre-calc they don't show you the limiting process, but in calculus you're supposed to learn how to do this using the limiting process. But I'll give an example. So this would be something like f of x equals 4 minus 3x squared over x squared plus 1. All right,
Okay.
so in this case, the degree of the numerator is 2, the degree of the denominator is 2, and you learned in pre-calculus that it's the ratio of the, say that
Or
again?
was it the coefficient?
Yes,
Or something like
exactly.
that?
So
Yeah.
it'd be minus 3 over 1. Okay. They're so the way you do it though in calculus is a bit different. So
Sure.
I'll just show you that here real quick. You end up dividing by the highest degree exponent, both the top and the bottom.
Okay.
And I don't know if you've seen this before, but this is like the official way to do it. That's correct. This is what's hidden from you in pre-calculus.
Oh, gotcha. I definitely haven't seen that one.
So you end up just dividing each term by it. And you'll see that obviously there's some things that cancel. If this is confusing, you can just forget it after the lesson because you may not see it again. But it ends up being the limit x approaches infinity, 4 over x squared minus 3 over 1 plus 1 over x squared. And then at some point in the course, you're told that the limit of 1 over x to the n, so the limit x goes to plus or minus infinity, 1 over x to the n is always 0. And that's useful because it tells you that, let me grab this here, that this 4 over x squared goes to 0, this 1 over x squared goes to 0. So this whole limit becomes minus 3 over 1, but it's exactly what you just told me. It's the ratio of the leading
Okay.
coefficients.
Gotcha.
So they just tell you this in pre-calc, but you're supposed to in calculus be able to do this. Like on a chapter 1 test, when you're doing limits and stuff, they tend to give you a problem like this to look at. And there's variations on it. This is just one example. So case number 3 is when in terms of it's the slant asymptotes. If you recall those, but an example would be something like x squared minus 3 over x plus 1. So your degree of your numerator is greater than your degree of your denominator.
Okay.
And in pre-calculus, you ended up having to use polynomial division to divide.
Right.
But you do not have to do that here. But you are supposed to do the whole dividing by the highest degree power. But is generally in these problems, the limit as x goes to plus or minus infinity, f of x, it always goes to plus or minus infinity because the graphs either shoot up in one direction or the other.
That makes sense.
From the slant asymptote, whichever it ends up being. Sorry, I know that was a little bit rushed here. I was just trying to.
No, that's absolutely fine.
In.
No, that's absolutely fine. But at least I have an idea of like how it's supposed to look like eventually, like when it comes to these questions, which is perfect. No, that was perfect. I really appreciate it.
Great. So let me do the a little bit of the sales side of it really quick here. Make sure I've got this pulled up. So for the majority of my customers, they like to go to my website and book tutoringbymatthew.com. You probably saw that in the email I sent you earlier. If not, you can go here. So you go to schedule, meet with Matthew, and then you just choose the date and time of the lesson that works best for you.
Okay.
So it's pretty convenient. Most of the time you can book a week out if you want. Just with the holidays, it's a little, I mean, but you can see there's stuff next week
Booked out, yeah,
available. So
yeah.
I also do the following. If you want like every, what is today? Tuesday at 6:30. I can't promise that at the moment, but like, let's just say you wanted like every week at this time and this time.
Yeah,
I can manually schedule it so that you always have those times available for you. The lessons are 50 minutes. There's a couple of reasons for that. I did some research into it. 50 minutes is about the extent that most students can handle. If you feel like you want more time than that, I can make accommodations for it. It also gives me a little break in between lessons as well. Like I said, I send you the notes. There's a screen recording of what we did today, so you can always have access to it. I also do a lot of stuff on social media. So if you like have a question and you don't need a full lesson, I'll sometimes throw up a video for you or just answer your question on like Instagram, throwing up the solution to help you out
for
for that.
sure, yeah. No, that's absolutely fine, that's excellent. I hadn't looked over the website, what's the rate looking like for 50 minutes?
So it's 35 for the hour, and you can, so when you schedule, you pay, and then it automates a booking link. Like I don't get involved anymore with the scheduling.
Okay,
So it's all automated. It's kind of like when you go to Amazon, you buy something, you
yes,
click
sir,
pay and you get a link. Most of my customers find that's pretty appealing. But if you've got a special situation, you can just let me know
for
and
sure, man.
we talk about
I
that.
Yeah, for sure. So, I mean,